I'm just going to summarize the extreme value theorem, Rolle's theorem, and mean value theorem for your notebooks. EVT is the extreme value theorem, RT is Rolle's theorem, and MVT means the mean value theorem. Oh, let me focus this a little bit. There you go. Extreme value theorem, Rolle's theorem, mean value theorem. First, the extreme value theorem. I'm just going to draw just a random function starting up here. It'll curve around and come maybe way down here and then come up and then end right here. All right, here's A, here's B. That's the endpoints of our interval. And the extreme value theorem just says that if this is continuous and differentiable on this interval, which it is, then there must be a max and a min somewhere within that interval. And we're going to find them. Find the extremes. So to find the extremes, what we have to do is find what f of A is. We have to find out what f of B is. And then we have to find the derivative, set it equal to 0, and find f of those x values. So to find the extremes, first we do f of A. It's equal to something. Then we do f of B. It's equal to something. And let's just put some real numbers on here. I'll just put specific points at all the potential places. So let's say this is 1. Let's say this is 4. Let's say this is, I don't know, 8. Let's see up here. Let's say this is 9. And let's say this is 12. These are just random y values that I've just guessed. All right. So we find f of A and f of B. Well, f of A in this picture is equal to 4. F of B in this picture is equal to 9. And then that's the first job. The second job is we have to find f prime of x. This is f of x. F prime of x, so we find the derivative of it. We set it equal to 0 and solve for c. And there might be more than one c value. Well, what all this is saying is, where is the derivative equal to 0? Well, it's equal to 0 at all of the local mins and maxes. So here's one place right up here. I guess I'll call that C1. And then here's another place down here. Let's call that C2. And then here's our last place where the derivative is equal to 0. We'll call that C3. So, oops, that's step 3. So f of A is 4, f of B is 9. We find the derivative, set it equal to 0, solve it for c, and there might be many of them, like there might be 3, like in this example. And then we have to do f of C1, f of C2, and f of C3. Maybe we won't have a graph. Maybe you have to do this all algebraically, which is a lot of times the case. So what is f of C1? Well, here's C1 up here. It looks like it's 8. And f of C2, that's equal to 1. And f of C3, that's equal to 12. And then you just look down your list of numbers, and the lowest one is the min and the highest one is the max. So this is A, B, and C. So we have step 1, step 2, step 3, and then there are 3 sub-steps within step 3. And the highest is the max, lowest is the min. So it looks like here's our lowest right here, our min. C2 is our min. C2, whatever that value is, comma 1. So the minimum value of this function is 1, and the highest, oh, the highest is this one right here. 12 is the highest number. So that would be C3, comma 12. That's the max. And that's the EVT in the nutshell. But make sure you have to find f of A and f of B, because f of A might even be lower, or f of B might even be higher than the max, or, you know, it could be anything, but you just have to find the y values of the endpoints and the y values of all the places where the derivative goes to 0, and then evaluate all these numbers from high to low. Rolle's theorem. Rolle's theorem says you have to have f of a equaling f of b. And if f of a is equal to f of b and the function is continuous and differentiable, then there's some value of c, maybe more than one. There's at least one c where the derivative is equal to 0. What does that look like graphically? Well, let's say this is A and this is B. They have to be horizontally equal to each other. I don't know, let's call this 3. So f of A is equal to f of B. Well, this function could do anything in between A and B. It could curve around 100 times, or it might just curve up and down once, or it might even just go straight across. But let's just say this curves around and around and around, and it gets back to here. So this is a smooth continuous function, differentiable. So f of A is equal to f of B, which is equal to 3. And then you have to find f prime of x. You set it equal to 0. So step 1 is just making sure the y values are the same at the endpoints. Step 2 is set the derivative equal to 0 and solve for c. Because there has to be at least one value where the derivative is equal to 0, otherwise you couldn't make it from A to B. So here's one value of c, we'll call him C1. Here's another value of c, we'll call him C2. Here's another value of c, we'll call him C3. And here's another value of c, we'll call him C4. There are actually 4 values of c in this particular Rolle's theorem. 4 different values of c where f prime of x is equal to 0. And that's all Rolle's theorem says, is that somewhere in between there the derivative goes to 0. And then the mean value theorem summary. The mean value theorem says that if you have a continuous differentiable function, let's say it looks like this, and let's say this point right here is A. This is a big long function. Let's say this point right here is equal to B. The mean value theorem says we're going to calculate the slope of this line between A and B. And this line between A and B is called a secant. That should be a geometry term you remember. So the slope of this secant is just the slope formula, y1 minus y2 over x1 minus x2, or in big boy terms, f of b minus f of a all over b minus a. That's just a slope formula. So this slope is equal to something. And the mean value theorem says there's at least one value of c in between a and b where the slope or the derivative is equal to that slope. There's at least one. Oops, if I can write. So let's just go along here and let's see if we can figure out how many values of c there would be where the slope is equal to 0. So we're starting at A, the slope is pretty steep, coming along here. Oh, it looks like this point right here. Looks like this point would have a slope that's the same. As long as it's parallel, it'll be the same. So then you're coming around here, slope goes negative. Oh, and then you come around here and it looks like the slope goes the same here. So here's one value of c. Here's 2 values of c. Keep going, slope, 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 slope. Oh, here's another value of c right here where the slope is equal because it's parallel. Go along, coming around. Oh, looks like right here. So it looks like there's 4 values of c where the slope is the same as that original slope. Here's one right here. This x value, we'll call him C1. Here's another value, we'll call him C2. Here's another value, we'll call him C3. And here's another value, we'll call him C4. In this particular picture, there are 4 values of c that has the derivative equal to that slope. We haven't actually come up with an algebraic problem yet that has 4 values of c, but there could be 4, there could be a lot. So in this example, C1, C2, C3, and C4, those are all x values, by the way, have the same derivative as the slope of the secant between A and B, those x values right there. So you're solving for those x values, 1, 2, 3, 4. And that is the mean value theorem in a nutshell. The next thing I'm going to talk about is the difference between increasing versus increasing functions or intervals within that function. First of all, if f prime of x is positive in the interval, open interval from A to B, then the function is increasing. That just means the graph is rising. If the derivative is negative, I think you probably already know this from other talks. If f prime of x is negative in the interval from A to B, then the function decreases. And if f prime of x is equal to 0, and it could be equal to 0 on an interval, it means it's flat, straight across from A to B horizontally, flat, then it's constant. On that interval from A to B. Oh, on the intervals of increasing are closed intervals. So it's increasing on A and B. It's a decreasing function from A to B, closed interval, constant on A to B, closed interval. All right, on all of these, the function's got to be continuous and differentiable. So f of x must be continuous on the closed interval, CINT, continuous. Doesn't look right. On, whoops. And differentiable on the open interval, A to B. So that's just a caveat like the MVT and the Rolle's theorem and the extreme value theorem. So if we have a little example function here, let's say f of x is equal to, I'll just use the one that's in the book, x cubed minus 3/2 x squared. If we took a look at the graph of that function, it goes up, hits the origin, comes down, and goes like this. All right, so this function is increasing from negative infinity to this local maximum. It's decreasing from this local max to this local min, and then it's increasing from this local min all the way up to infinity. And if you wanted to take a derivative of this, f prime of x is equal to 3x squared minus 3x. If you set that equal to 0, factor out the 3x, you see that x is equal to 0 and x is equal to 1. And those are the 2 points on this graph where you'd have a local max, that's x equals 0, and a local min, x equals 1. So what you're going to do is, if you didn't have a graph of this and you wanted to know the general shape of this function, this original function, to see where it's going up and down and where, where it turns around, what you're going to do is that, I think I mentioned this before and maybe I gave you an example, you're going to set up a sine table Now there's no leftmost point and there's no rightmost point on this. This just goes from negative infinity to infinity. So what you're going to do is you're going to set up a sign table like I showed you before, and those are those x values where the derivative is equal to 0. So there's f prime of x table. And you just substitute a number that's less than 0 into this derivative and see if it's positive or negative. Well, it would be positive. If you picked like x equals -1, you'd have a negative times a negative, which is a positive. Here you can pick any number between 0 and 1. Like if you pick a half, you have a positive times a negative, which would give you a negative. And then you pick any number greater than 1, plug it into the derivative, and you'd have a positive times a positive, which would be a positive. And this is the sign table. And that just shows you the shape of the graph. And the shape of this graph means it's going up because the derivative is positive. It's coming down because the derivative is negative. And it's going back up because the derivative is positive again. Here's another function, example number 2. Let's say f of x is equal to x cubed. And we want to know the general shape of this, or we want to know where it's increasing and where it's decreasing. So you're going to do f prime of x is equal to 3x squared. You're going to set that equal to 0 and solve for x. Well, x is equal to 0. So there's only one critical value. These up here, these are called critical values. That's what we called them before. 2 critical values. There's one critical value here, x equals 0. So you put it on a sign table, f prime of x, and you put a 0 right in the middle. And if you look at this function right here, the original function, I'm sorry, this is an f prime of x table. So you're going to plug it into the derivative. If you plug a negative number into the derivative, it's 3 times a negative number squared, which is a positive number. If you take a positive number and plug it into the derivative, you get another positive number. So what happens with this graph is it goes up. It flattens out just for that point where x equals 0, and then it keeps on going up again. And you can probably imagine why. You know what the shape of x cubed is. It looks like this. This graph is always increasing. From this sign table, you can see the function increases, decreases, and increases just because of this sign table being plus, minus, plus. Increasing, decreasing, increasing. This is increasing and increasing. Okay, and then our last example here, let's say f of x is equal to this piecewise function, which is negative x squared when x is negative. It's equal to 0 when x is between 0 and 1. And it's equal to x minus 1 quantity squared when x is greater than 1. So you have 3 pieces on this piecewise function. And if you did a quick graph of this, negative x squared, and this is an open circle here, negative x squared looks like this for x is less than 0. F of x is equal to 0, which means it's just a flat line from x equals 0 to x equals 1. So there's the middle piece, left piece, middle piece. And now you have a right piece. This is a quadratic. This is just a regular parabola that's been shifted 1 to the right. So it kind of goes up like this. So what we have, we know from the graph it's going to be increasing, constant, and increasing again. But what if we didn't have the graph? We would have to do an f prime of x as a piecewise function. That would be negative 2x when x is negative. The derivative of 0 is 0 between 0 and 1. And the derivative of this is 2 times x minus 1 for x is greater than 1. Sorry about that beep. So it's just 2x minus 2. If you set this derivative equal to 0, you'd see you'd have a critical value of x equals 0 and x equals 1. X equals 0 here, x equals 1 here. So if you wanted to set up a sign table, 0 and 1 for f prime of x, if you plugged in a negative number into this derivative, negative times negative would give you a positive. This derivative is 0 here for this whole area between 0 and 1. And when x is greater than 1, if you plug in a number greater than 1, 2 times this positive number would give you a positive. So you know the shape of this graph would be going up, it would flatten out, and then it would go up again, just like what we saw when we graphed this. So that leads us to the conclusion that if f prime of x changes, and I think we wrote this before in our notes, but if it changes from plus to minus, which means the graph goes up and then it comes down, the critical value is a local max because it goes up and then it comes down. And if f prime of x changes from negative to positive, the critical value where that change happens is a local min, because the graph would go down and then it would come back up again, and that critical value right there is a local min. It could be an absolute max and an absolute min if it's a closed interval, but you're not sure about that. And then the last conclusion, if f prime of x does not change signs, at the critical value, if it goes from plus to plus or minus to minus, just like I showed you in one of those examples, then the critical value is neither a local max nor a local min. So you have really 3 conclusions here, 1, 2, and 3, depending on the change of the first derivative. So the first derivative table is a really quick and easy way to figure out whether you have local mins or local maxes at your critical values. And I think that's going to be it for today. Have a great weekend. Bye.